Okay, so I'm going to get started. For anyone who missed lecture on Monday, this is Organic 2 lecture. So the course website that I'm using is orgchemboulder.com, and that's where you can get a copy of the syllabus that I handed out a paper copy of on Monday. That's also where I'm going to be posting the chapter notes and a link to the lecture capture because these sessions are being recorded. Based on feedback from last semester's FCQs, I'm actually trying out something new with the lecture capture, and that is rather than having a shot of the entire board where you can like vaguely make out what I'm writing, I'm actually trying to super zoom in on whichever sector of the board I'm writing on at that time. So if you see me switch sections and not fiddle with this control panel here, if someone could shout out a reminder, because it's probably going to take me a little bit to get used to it, but I'm hoping I can sort of like pan across as we go along, and then if you have to miss lecture, you can actually read what I'm writing instead of like listening to me talking and then having to follow along in the typed notes. Okay. And then the other site that we're using is canvas.colorado.edu. That's where I'm posting grades. And that's also where, as of last night, the link to our course sapling page is now open. So I posted instructions in there. Has anyone actually followed through on those like in the last 12 hours or so since I linked it? No? Okay, so I'm hoping that works. We had a little bit of a hiccup getting it set up last semester, but should be good to go. And the sapling has sort of a few kind of warm-up exercises in there. I guess, did anyone not use sapling for OChem 1? Okay, cool. I'm seeing a few hands go up. So there's a few sort of intro assignments in there that are basically like how to draw stuff in sapling so that the system won't yell at you. Even if it's technically correct, and I would accept it on an exam, sometimes sapling's a little bit weird in how it parses things. Maybe like atoms look like they're connected to a bond, but they're not really. So especially if you had issues in the past or if you're unfamiliar, I definitely recommend going through the practice exercises in there. And it also has sort of an OChem 1 review thing in there that I'm going to open up later this morning. Neither of these things are for a part of your grade, but you know, if you're feeling a little bit rusty or you want a little bit more practice, it wouldn't hurt to go through either of those things. Okay, questions about those? Okay, and then the other thing that we're using as far as online learning tools is Packback, which I haven't set up the integration with Canvas yet. I'm hoping I'll get that sorted out in time for Friday's lecture because that way I can sort of do a little intro slide thing about it, but I'll let you guys know. Okay, cool. So my plan for today is do a little bit of OChem 1 review. Quick show of hands, I guess, who here did not have me for OChem 1? Okay, a bunch of people, because I got a couple of emails coming in from people who had looked over my chapter notes for OChem 1 and said they felt real shaky on some of the chapter 11 chemistry, especially cuprates plus epoxides. So I think I might do actually sort of a quick review of that topic and then maybe do some problems off my OChem 1 final that kind of use that chemistry just so you can see like how to actually plug it in and do stuff with it. Does that sound good to anyone? Okay, cool. So I'll do that first, and then like if anyone has any specific topics they want to go over, we can do that, or I can just like go around through the exam at whatever looks like a decent review of stuff. Okay. So out of the chapter 11 stuff, cuprates plus epoxides is probably the most useful and versatile reaction that we covered in that chapter. And the reason for that is that unlike pretty much all the other chemistry that we did in OChem 1, which is like functional group interconversions, maybe turning like an alkyl halide to an alcohol or like an alcohol to a carbonyl or stuff like that, this is the only one that reliably and consistently makes new carbon-carbon bonds. So that's useful because if we're trying to do a synthesis and we're trying to build up some framework of a molecule, we're going to have a really hard time doing that if we can't stick together different groups of carbons. So things that make carbon-carbon bonds are probably going to be like, the more ways we have to do this, the more skills that we have in our synthetic toolkit and the more things that we can actually build when we're trying to do syntheses. Okay, so before I get into cuprates, let's look at epoxides plus other stuff. So epoxides, the gist is actually, let me actually draw the carbons explicitly. Okay. So it's a 3-membered ring with an oxygen and 2 carbons in it. And you can replace any or all of these H's with other with other R groups coming off of here. So you can have like, 4 methyls or like a butyl coming off of there, but that's kind of the simplest possible epoxide, is just this 3-membered ring. So we have actually 2 different types of reactions that are going to do stuff with epoxides. They both fall under epoxide ring opening. Real quick, can you guys up to the back read this okay? Okay, cool. Yeah, sorry about my handwriting in advance. It's kind of crap, but if you can't read anything, please let me know. Okay. So the 2 kind of categories of epoxide ring opening that we're looking at are either in acid conditions or base conditions. Okay, so an example of an acid epoxide ring opening might be, and you'll notice here I'm actually doing a more complicated epoxide, and there's a reason for that, because the difference between acid and base is the difference of whether you're going to attack at the more or the less substituted carbon. So in acid, do you guys remember whether we go more or less substituted in acid? Those of you who've seen this before? Yep, more substituted. Okay, so in acid we're going to attack the more substituted carbon. So the reason for that is, well, let's go through the mechanism and sort of puzzle it out. So a setup for this might look like we've got an epoxide, we just need some source of acid. We can actually just be real vague and say like H plus on the arrow. If you want to be more specific, you could say like trace H2SO4 or some other kind of just proton source. And then we want something that's nucleophilic enough to come in and attack what we're going to make after the acid gets in there. So I guess one example might be, let's say methanol. Okay, and that could be some other nucleophile, but the caveat is it's something that's got to be able to exist in the presence of acid. Like you wouldn't be able to use MEO minus for this reaction because it would immediately react with the H plus and you wouldn't have MEO minus anymore. So is
it fair to say the nucleophile can't be charged then?
There are some really weak base nucleophiles that you can do this with. So one other example would be like HBr, which is its own proton source and also its own nucleophile source, because then you make Br minus that could come around and attack. But yeah, for the most part, you're right. It's like nothing that's more than like, I guess like it also depends on the pKa of what our generic proton source is, which since I'm being vague, we don't know for sure. But yeah, like if it is minus charge, it's got to be real weak base for this to work. Okay, so to get this started, and I'm going to draw my lone pairs in explicitly here, we know that we have an H plus here. We also know that we have a nucleophile that's pretty weak. So I guess, let me add a little note here, or other weak nucleophile might be a better way to phrase that. So nothing strong, nothing very basic. Okay. So we've got a nucleophile that's not very good at attacking stuff. We've got this molecule that's not very electrophilic. It's not great at getting attacked. What we can do to make this reaction kind of I guess kind of encourage it along, is we can turn this thing into a better electrophile, make it more attackable. And that's where the H plus is going to come in. If we stick a proton onto this molecule by having the lone pairs come out and attack the H plus, suddenly we have what looks like a much more attackable, much more electrophilic molecule. Okay, so now this is looking like a good enough target that even our crappy nucleophile over here, the MEOH, can come in and do the attack all right. So now we need to wonder where the attack is actually going to happen. And this is actually where we can tie things back a little bit to the Chapter 5 chemistry. So if you guys remember, let me do a little side box over here. If you guys remember, if you take an alkene here and you do a reaction with Br2, that attacks the bromine, kicks out the other bromine, and you make this three-membered ring. Okay, so this, if you look at it, is actually real similar to this protonated epoxide. It's got a three-membered ring. It's got something that has a positive charge because it would like to have one more lone pair than it currently has. And so when we did this in Chapter 5, we attacked the more substituted carbon. And that's because this plus charge, you can actually show like sort of pseudo-resonance forms for it. But the gist of it is this plus charge is getting parceled out a little bit to the two carbons of the ring. And out of the two of them, this one is more equipped to carry a delta positive charge, so it's going to have a bigger delta positive charge. So I'm going to show like big delta positive on this carbon and teeny delta positive on that carbon. So when the nucleophile comes in this case it was Br minus, I guess the biggest plus charge on the molecule is the Br plus here. It, I guess, could attack there, but then would pretty much go right back to where we started as the three-membered ring falls apart entirely. The only productive way forward to actually get different products, which is what we're showing with this mechanism, is to attack something else positive charged. And out of the two carbons, this one looks like the better target. It's the more electrophilic of the two carbons because of its bigger delta positive charge. So this comes in, attacks that carbon. Didn't leave myself much room there, but this bond pops open and goes onto the bromine. And you end up with this sort of attack, or this sort of structure. And I guess because I used two bromines, you can't exactly tell as far as like what connects where, but this bromine here is the newly added one that went to the more substituted carbon. Okay, so questions about that? Okay,
So how favorable is that intermediate step because of you're using the more substituted carbon as the source or where it's being attacked, but wouldn't there be steric hindrance if you had like a large base?
Yep, there absolutely is. And so like doing this attack, I guess like if you did the energy diagram, like this might be kind of a high barrier, but it ends up, especially if you've got like Br2, which is fairly reactive around, it ends up being thermodynamically like favorable overall, so that even though it's got a high hurdle to get over to get there, it still eventually favors going to this product. We're going to talk a bunch more about energy diagrams and favorability later on, but yeah, sterics is definitely always a thing to check for, but in this case it turns out not to be as big a deal. So
like experimentally you have to be, like if we were writing it out, like we'd have to be very conscious of the size of the base that we were using in our
Yeah, and I guess for this particular reaction, because there's sort of positives and delta positives involved, sterics ends up not being such a big deal. I guess the description that we use to kind of describe this is it's electronically controlled or under electronic control. Fit that in over here. So in other words, the charge is what dictates the outcome of the reaction. Okay, so even if the sterics are not as good at the carbon that it goes for, a lot of the time if there's a big difference in charge density, that ends up kind of being more important than sterics. But that's not going to be the case for the other epoxide ring opening conditions, which we'll get to in just a second here. So good question, thanks. Oh, and also, sorry, while I'm on the topic of questions, if you raise your hand and I don't see you, please feel free to like shout out the question anyway. Sometimes I'm like looking around and there's enough people in here that I might miss you, so please don't hesitate to interrupt if you get something that's like related to what we're covering just then. Okay, so jumping back to the epoxide thing here, this is actually going to go pretty similar to the dihalogenation mechanism. So we've got our three-membered ring with a plus charge on one atom. The plus charge atom itself is not really going to be attackable in any productive way, but out of the two carbons it's attached to, this one here is going to lead to a new product and is also the most attackable. So this one has the biggest delta positive. So here, whatever our nucleophile is going to go in for that carbon, kick the ring open, just like with the bromonium ring here, and that will get us to okay, so the big difference between this and the two bromines reaction from the alkene stuff is that here we attacked with a negative charged thing, and so immediately after the attack, that negative bromine went to being neutral. Here, we attack with something that was neutral already, so after I do the attack, that's actually going to have a plus charge on it. Okay, so what we need to do to clean this up afterwards and get to a neutral stable product is we just got to clean up that plus charge by pulling a proton off of there. This may or may not be how your OChem 1 professor did things, but I guess there's two different ways that I'm okay with you showing this. One is you can be specific about what's coming in to deprotonate. So pretty much the only base, even if it's not a very good base that we have around, is MEOH. I guess you could also show another molecule of epoxide starting material coming in and doing this, and that would be fine too. But you can show a specific deprotonation as long as it's reasonable by pKa's. So MEOH could come in, take that proton, and kick the electrons back onto the oxygen, which would give you your second lone pair back, which would give you a stable neutral oxygen. Or I am also okay with you showing ambiguous deprotonation. So leaving it kind of vague and unsaid what is actually coming in and taking this proton. So to do these same two steps down here, but left less specific. Let me draw that bond out a little bit more clearly. Okay, so I'm also okay with you showing just this bond breaking onto the oxygen. And it's sort of looking like the proton is just left to drift off on its own with a plus charge. In reality, that doesn't happen, but a lot of the time proton transfer is kind of a poorly defined step, and there's multiple different things that could come in and take this. So a lot of the time people are like, you know what, it doesn't really matter. Just don't bother showing anything specific and it's fine. So it gets us to the same place either way. But you don't have to be picky about how you show it. So either one of these things, if you drew it on a test, would be totally fine. Uh-huh.
Do you emphasize showing both products or just ignoring the stereochem?
Good question. So in this one, I'm showing connectivity only. If I'm getting into stereochem, then we'd have to worry about like what the chirality on that thing was to start out with. So yeah, let's hold off on that for a little bit. Yep. Okay. So other questions about that one? Okay, cool. So that's acid conditions. I think if I do base conditions over here, it's going to make the board kind of confusing on layouts. So why don't I pan over? Come on. Nope. Okay, anyone watching this at home is going to see me like pan way off to the wrong side of the board. Hold on. God damn it. Okay, one more. All right, that ought to do it. Cool. Okay. So acidic conditions is one way we could do epoxide ring opening. The other option is basic. And here, we are going to attack the less substituted carbon. Okay. So, a way you could set this up, for example, let's use the same epoxide again because it's nice and simple, but it still has a more and a less substituted side. Here, we don't use any kind of strong acid to protonate the epoxide. We just need sort of a stronger base. So since we're not boosting the strength of our electrophile by protonating it first, we're going to have to boost the strength of our nucleophile by using a stronger, more nucleophilic base. So let's use MEO-. And again, there's different levels of being specific you could do here. We could actually specify like a counterion like MEONA if we wanted to be like a little bit pedantic, but this is kind of the useful part of whatever methoxide base that we're throwing in there. Okay, so we need this, but we also need something that, even if it's not a really acidic proton, can still like donate a proton later on. So, in other words, strong base, good nucleophile, but usually we're also going to throw in the conjugate acid of that strong base. So in this case, we would throw in MEOH as our proton source. It's not really acidic, but it can donate a proton if it has to later on. And also, the good thing about this is, once this thing donates a proton, you're just recreating more of the MEO-, so you're sort of making more methoxide as you go along. So it's kind of a catalytic amount of methoxide is what you need, is all you need. Okay, so the mechanism for this one is we don't protonate this first. We just go right in for the attack because this nucleophile is already raring to go. So because we don't have a plus charged epoxide going on here, we are not under electronic control. There's just about no difference in charge between these two carbons. There might be a tiny, tiny bit depending on how the molecular orbitals work out. But at this point, we're more under steric control than electronic control. So in this case, the outcome is controlled by how much room there is around either of the two carbons. Phrase that. Okay, so it's more controlled by the space requirements around each carbon. Okay, so sterically, left or right, the two carbons of the ring, which one is sterically more accessible? Right, good, yep. Okay, so I'll just draw it from here. So this methoxide, when it goes in for the attack, it's going to attack here and pop that ring open. So you end up with O minus over here and OMe over here. A couple of things. One is that since we attacked with a negative charge nucleophile, we don't have to do that positive charge cleanup step at the end like we did before where we pulled a proton off. However, since we did not protonate our epoxide first, now we got to deal with cleaning up a minus charge, and we can do that by sticking an extra proton onto it. So this is where our conjugate acid comes in. We're just going to finish up our reaction and clean up our negative charge by having it rip an extra proton off of the conjugate acid. Okay, so like that. Alrighty. So those are kind of the two big categories of epoxide reactions. Questions about those so far? All right, cool. So this is a very roundabout way of getting there, but now we can look at epoxides plus cuprates. Okay, so this whole thing is a subset of basic conditions. Which means that we're going to go in for the less substituted carbon. But we're going to be doing it with something that acts a little bit specially. Those of you who didn't have me for OChem 1, did you cover how to make cuprates at all? Or do you want me to go over that real quick? Go over it? Okay. So first, you want to make a cuprate. And the way that we make them is from organometallics that we've been using previously. So we're going to make them from the organolithium version of it. So if we use, say, I don't know, ethyl lithium, what we're going to do is take that organolithium that we already made. And by the way, if you need a refresher on how we got this thing, it's basically from whatever alkyl halide, and then you hit it with lithium metal, and you need some sort of organometallic solvent. THF is by far the easiest default. So lithium THF makes you the organolithium here, and then we can take that organolithium and we're going to react it with copper with a single halogen on it. Doesn't really matter which one. I like bromine. There we go. If you want, you can also sort of restate that this has to be in some sort of ether solvent, so you can write THF on there. Although usually in practice, you would just start with the same batch of THF, throw some lithium into it to make this, and then throw some copper salt into it to make the next thing. So you don't really have to add any more THF as you go. Okay, so what this is going to do, and note that we are not really caring about reaction balancing a lot of the time because this is Gen Chem and we can get a little bit sloppy about stoichiometry. So what we're doing is, sorry, this is not Gen Chem, I should have said. So what we're doing is throwing two of the alkyl groups onto the same copper. So the copper now is going to take on a minus charge, and the lithium is going to have a plus charge. Or we could write this in a couple different ways. A lot of the time, especially if the R group is sort of big and complicated looking, we're going to draw it once, throw parentheses around the R group in a way that sort of cuts off the bond between the R group and the copper itself, and then just do a 2 there. That's another way of showing them. And then you can either do them charge separated or just like one right after the other is fine. Or you might see it written out. What's the 2-letter abbreviation for this alkyl group here? ET, yep. Okay, so these are all 3 different perfectly good ways to show this reagent. If you're unfamiliar with the alkyl group abbreviations, definitely make sure you polish up on it. But to be honest, it's kind of common sense. Like if you see PR is going to be propyl, Bu is butyl, Me is methyl. Okay, so we've got our cuprate here. Now we can react that with an epoxide. You know what? I'm actually going to draw out both groups explicitly for this one. Okay. So what's going to happen here is one of these R groups is going to go and attack the less substituted carbon of the epoxide. So if you want to show the actual mechanism, to be honest, this mechanism involves transition metal chemistry and is not exactly the same as it would be for a Grignard or a lithium. So this is a little bit hand-wavy and nonsense, but we'll sort of get more in depth on how transition metal stuff works when we get halfway through the semester. There's a chapter about it. This is good enough for now, though. Okay, so we attack the less substituted carbon, pop the ring open, and we end up with, I guess the cuprate kind of, the copper goes off with its one remaining R group. But what we care about at this point is, okay, so our new R group here, this ethyl, these two carbons become these two carbons, which just glommed onto the less substituted carbon of the epoxide. Okay, so that gets us to here. And now at this point, we're going to do something similar to the regular basic conditions, where we have some sort of acid source, and that can go take a proton. All right, and there's some important warnings about that too that I'll cover in just a second here. Okay, so questions about that so far? Okay, cool. So, how you would write the overall reaction for this? So unlike up here, where we did base catalyzed or basic conditions, where we actually had our proton source there present during the reaction, because you know, if MEO minus and MEOH react with each other, you can't even tell. They're just swapping a proton back and forth between two methoxides. Here, we actually do have to be fairly careful. We can't let the organometallic and the proton source be in the same place at the same time because they're just going to kill each other off. So, So we're going to have to do this as a two-step reaction where first we add the cuprate, then we add the proton source later on. So in other words, we're going to do the reaction with the actual cuprate and the epoxide, and then we're going to do like a mild acidic workup is how we would call this. So and the acidic workup is almost always going to be just in water with a little bit of acid. So another synonym for that is aqueous workup. And in fact, a lot of the time people will just write WKP on the arrow for step 2, like just work up. That's kind of implied, put it in water with some acid in it. Okay, so we would write this overall as, assuming that we're still making our epoxide like the main character of the reaction, I guess. We would have our epoxide here. We're going to do step 1, whatever cuprate we have. Might as well be explicit about solvent. Let's write THF on the arrow there too. And then step 2, we're going to do H3O plus, and that will get us to this final product that I showed up here. Okay, So that's if we're kind of doing this from the epoxides point of view. In other words, like especially if we're doing some kind of synthesis where we like start out with some other reagents, do some things to it, maybe go through a few steps and eventually get to the epoxide. And then from the epoxides like point of view, the cuprate comes in, does something to it, and we're here. We could just as easily show this from the other point of view in the reaction from the cuprates point of view. Where maybe the cuprate is like your main character of the synthesis or whatever. It's something that you've spent a few steps putting together. So we're coming in with this. And then the epoxide would be like this other reagent that shows up, and so we would write that on the arrow. So epoxide here, and then if you want, you can also specify THF, although having this here is kind of like, you know, there's going to be THF or some kind of ether solvent around already. And then aqueous workup again. Gets you the same thing. Okay, so I know we're used to seeing reactions written out of like, here's our starting material, here's the stuff on the arrow, here's the product. But think of this as like, I don't know, a story from a particular molecule's point of view. Like chapters 4 and 5 were all about things that happen to alkenes. But, you know, from the other reagents' perspective, like maybe they're sort of the main character. You could just as easily write any reaction that was seen with any reagent before the arrow, and then all the rest of the stuff on the arrow, and it's still like the same reaction. It's just which part we particularly care about is the one that we're writing before the arrow. And usually during a synthesis, that's going to be whatever we've put additional steps into making ahead of time, if we have, or whatever we're given as a starting material for that synthesis. Okay, so questions about that? All right, so how to actually use this? The important part. Okay, so during these reactions, what we're doing is making a new structure like this. I guess those of you who did not take OChem 1 with me, did you see like the synthetic disconnect kind of convention, like the little cut here line on the molecule? No? Okay, I might do that real quick. So the disconnect is kind of like, where did we make or break a bond during the previous step? So let me write this down first and then I'll show you. So this makes a disconnect 2 carbons away from the OH group. So for example, in this reaction, say this product here, our disconnect was the bond that we made during the previous step. Or in other words, if we're working backwards, this is the bond that we're going to have to snip apart in order to step backwards through time, kind of. So this is our disconnect. This is the ethyl group that came in from the cuprate. And if we go 2 carbons further away, we've got an OH group. And it's important to point out the OH group is going to be 2 carbons away from the disconnect on the side that came from the epoxide. So looking at this, if I am told to make this molecule from a cuprate plus an epoxide, I'm going to go 2 carbons away from the OH group. I'm going to snip it right there. And then I'm going to say, okay, the side with the OH group on it, that was my epoxide once. And the other side with nothing on it, that was my cuprate. So that's my epoxide half. That's my cuprate half. Okay. So let me show kind of a synthesis problem. Let me pan the camera. Yeah. Okay. This is actually modified slightly from my exam. Okay, say I'm trying to make this thing happen. All right, so I'm looking at this. I know that I need to make a carbon-carbon bond, basically coming off of this carbon, because I didn't have any, extra groups dangling off of here in the first place. So in the final product that I'm trying to make, my disconnect line has got to be there because that's the new carbon-carbon bond that I'm making. Does that make sense to everyone? Or any questions about that part? Okay, cool. So this is the new bond I got to make. So looking at this, I've got a disconnect, and then I go 2 carbons away, and I've got an OH group. So right away, I am expecting that this half must have come from an epoxide. This half must have come from a cuprate. Okay, so now I just need to set it up so that that works. Pretty much I can just do the step immediately prior to this where, all right, so here's my cuprate. I got 2 of this entire ring part dangling off of the copper, the lithium. And I know that I'm drawing the cuprate before the arrow is like the main character because this ring obviously is going to match up with like the ring that I started out with. So I'm going to do some stuff in between now and then to figure out how to make this from the starting material I was given. So that means my epoxide is like the one that comes in on the arrow here, in other words. Okay, so the epoxide that I'm going to use is pretty much just going to be these 2 carbons plus the oxygen of the ring. So this one's relatively nice and simple. Just this epoxide is all I need. And then step 2 is going to be the workup. So like that. Okay, any questions about how I figured out that step of things? Okay, so I haven't finished the synthesis. I haven't written out how I'm going to get from here over to here in the first place. But I know that based on where the disconnect is and what my functional groups look like, this has to be a step that happens at some point in the reaction leading up to this product. Okay, so then I just got to finish it up. I got to make this from the alkyl halide. What a coincidence. That looks like just like what I wrote over here with the lithium. So I'm going to lithium THF first. Badoom. And then copper, halogen, THF, make the cuprate, and then I'm good to go. All right, so this is kind of like the obvious disconnect for cuprate plus epoxide. Anything similar looking to this in terms of layout? So on the actual exam, I didn't have an OH here. What I actually had was a BR here. But it's still the same kind of logic. You got whatever functional group on the second carbon away from the disconnect. So that looks like cuprate plus epoxide. And then if it happens not to be an OH specifically, you might have to do a little bit more work to get that functional group to be what you want it to be. So on the actual exam, I had you do one extra step where I wanted a BR there instead. So then the last thing you have to do is just do an OH to BR, which there's a couple options, but PBr3 is one of them. Okay, questions about that? Yeah? No, it goes away during the reaction. It actually leaves as a waste product with the other lithium because you're using 2 of these, so there's 1 lithium that get lost. So yeah, it's gone by the time you actually do anything useful with it. Mm-hmm. Okay, other questions about that one? Okay, so I still got 5 minutes. Okay, let's do a similar one. Okay, so this is 3A on my final. At least it is by the time you add this last step in here. Let's look at 3D because that's kind of the other way around. Okay. Sorry, question? Okay. So same starting material actually for this one. And we want you to make this out of it. Okay, so again, we're making a new carbon-carbon bond at some point during this reaction. That new carbon-carbon bond is going to be here. So that's where we draw our disconnect line, our snip here line. So looking at this, just like before, I have my disconnect line and it's 2 carbons away from the OH. But now the OH is on this left half of the molecule. So this must have been from the epoxide originally. So that's the epoxide, and this half is the cuprates. Okay, so with that in mind, I sort of have an idea for how I'm going to set this up. We do actually want it to have the OH at the end, so this is actually good to go to make the immediate previous step be just straight up cuprate plus epoxide. So, again, the main character molecule is going to be whatever I built at some point out of this 5-membered ring. So it's going to have to look like this now. So now my epoxide is kind of the thing before the arrow, the way that I'm writing it out. Okay, so the cuprate that I'm bringing in is going to have a 3-carbon chunk that comes off of it. So 1, 2, 3, and then copper. Okay, so in other words, this would be dipropyl cuprate. I don't really care about naming, but there's a couple propyls on there. And then lithium and THF. And then H3O plus again. Okay, so quick sanity check. I guess I should have done this up here, but it turns out not to matter. You want to also go through and make sure that when the cuprate plus epoxide step happens, are you actually going for the less substituted carbon? Because if you're not, then there's a problem. But in this case, it kind of doesn't matter. They're both equally substituted. In this case, it also doesn't matter. They're both equally substituted. So I kind of gave you a little bit of an easier time there, so you don't have to worry about steric control or anything. Okay, so we got our epoxide, we got our cuprate, everything looks good. We had a propyl group, we got everything where we want it to be, and we have the OH at the end. So that step's good. Now we just need to figure out how are we going to make this from the starting material we were given. What's probably the best functional group to have as the immediate precursor to an epoxide? Alkene, actually. Yep, I heard a few people say it, yep. So alcohol, sort of, I guess if it's a halohydrin where you've got an alcohol and a halogen on there, then you can make an epoxide too. But the easiest one, well here, I'll cover this way first and then we can, if we get time, look at the other option. But probably the easiest way to get there is start with the alkene there, which if you look at it, both of these 2 carbons of what's about to become the epoxide have a functional group handle on there, so we have access to both of them. And then MCPBA. MCPBA gives you the epoxide, and there's a few other options there too. So this is a peroxy acid. Pretty much any peroxy acid will do this, but MCPBA is just nice and easy to handle. But all peroxy acids are basically carboxylic acids with an extra O stuck in there. So that O is going to be what comes off and makes the ring during this reaction. Okay, so pretty much any peroxy acid, but you guys are actually going to use MCPBA next week to do an epoxidation reaction. Okay, and then the final thing to tie it together is we got to convert our alkyl halide to the alkene. Doing an E2 elimination is probably the easiest way. Tert butoxide is probably the best choice for that. Okay, so I'm out of time, but please feel free to let me know if you run into any issues sort of going over the OChem 1 material. And then the Chapter 14 notes are posted on the website, so I'm going to start those on Friday.
Can I ask you